for extension of the spring, there is a force which is created within the spring that tries to bring the spring back to its original shape and size. And this force is called a restoring force, right? So against the restoring force, we have to do the work either to extend or to compress a spring. This is called restoring force. So we are actually doing a work against the restoring force which is created within the spring. And that work is stored in the form of a potential energy. That is why when a spring is extended and left free, the spring comes back to its original shape and size. Because when the spring is extended, we did the work, and that work is stored in the form of energy. When it comes back, that stored form of energy is utilized by the spring to come back to its original shape and size. Understand? This is the condition about elastic potential energy, right? And the force, the pulling force applied is always directly proportional to the extension produced. So this is chiefly called as a Hooke's law. According to Hooke's law, you for a spring or a string, elastic string or elastic spring, we can say that the load is directly proportional to extension. Load produces an extension proportional to it. This is called Hooke's law. What I say? Load means force. Force produces an extension proportional to it. When we apply force on a spring or a spring, the extension or compression which is created within the spring is directly proportional to the amount of force applied. Am I correct? So what we can write is F is directly proportional to extension or compression, or F is equal to a constant K, small k into x, where this K is a constant proportionality called a spring constant. This is called a spring constant. Spring constant K is equal to F divided by X. F can be taken as restoring force because when we are pulling a spring tied to a rigid support, then the same amount of force is created within the spring. That is also same value. That value is called restoring force. Actually, we have to say that the spring constant K is equal to the force applied by extension or restoring force created within the spring per extension. That means restoring force or the pulling force per unit value of extension produced in the spring is called spring constant. For unit extension, what is the force needed for? Unit extension means 1 centimeter, 1 meter, etc. extension or compression. What is the force required is what is called a spring constant. So spring constant is a physical quantity. Spring constant is equal to F by X. In this expression, if X is equal to 1, if X is equal to 1, then K is equal to F fully, right? X is equal to 1 means extension is equal to 1 meter, 1 centimeter. For that, what is the amount of force required, or what is the amount of restoring force created within the spring? Both are same only. When we pull it, the inside of the spring, a restoring force is created. Both are same only, right? For unit extension, the amount of force required is called what is called a spring constant. So spring constant tells us the spring, whether the spring is a hard spring or a soft spring. For a soft spring, the value of K will be very, very less. For a hard spring, the value of K will be very, very high. Because for daily purposes, so many places in devices and also in very big machines, we use springs. To study about springs is not a loss, because many places, even in a ball pen also, we use a spring. So spring is a useful thing to, that is why we are studying about springs today. And now you have studied, a spring means every spring is elastic spring. For any elastic object, we can apply Hooke's law. What is Hooke's law? According to Hooke's law, the load produces an extension proportional to it. That means F is directly proportional to extension or compression. So F is directly proportional to X, or F is equal to a constant K into X, where K is called what? Spring constant. The unit of spring constant, that is Newton per meter. This is Newton, this is meter. Therefore, unit is what? N, m raised to minus 1, Newton per meter. So this is about the spring constant. Knowing the spring constant, we can say that whether the spring is a soft spring or a or what? Or a hard spring. Next is expression for elastic potential energy. Gravitational potential we have already calculated. Now what I'm going to calculate is elastic potential energy of a spring, right? That is the next topic. So let me write the topic on the top of this board. What is this? Elastic potential energy. Elastic potential energy of a spring. Elastic potential energy of a spring. A spring is having an original length. Suppose a spring has an original length like this, okay? This much length it has. Now suppose the spring is extended by the application of a force like this. Up to this much it is extended. From this position to this position, the extension is equal to x by the application of a force capital. So this is a rigid support. The spring is fixed at a rigid support, and it has an original length L. Now it is applied with a pulling force, so that the spring is extended in the direction of the pulling force by a value x, right? This is the condition, right? So now what is the force? Now we can say that force F is directly proportional to x, we can write, because according to Hooke's law only we write, because every spring is elastic spring, because spring is not made by copper or gold, but is made by steel, because steel is more elastic than gold and silver, etc. Right? Spring is actually made for that only. Spring is always made elastic only. So all elastic bodies we can write what load is proportional to extension. Load produces an extension proportional to it, or F is equal to X. What is the total force here? F is equal to K into X, we can say. So it is pulled into a certain condition, and it is not left free. At that time, the force acting is equal to K into X. In this stage, suppose that we are giving another small value of extension in the spring, that value is equal to dx. Already a force is applied, that is equal to F, right? It has come to this position from the equilibrium position. It has been extended, so that the force acting on the spring for that extension is equal to K into X. At this position, at this final position, suppose the spring is extended by a very small value dx. What is the force then? F is equal to Ks. Being in that stage, suppose an extension produced this is a very, very small value, then the change in force is negligibly small. So being force is equal to K into X at that stage, if a small extension is also made in the spring, then the small work done for that is given by dW. dW is equal to F into dx, but F is equal to Kx into dx, I can write. For a very small extension, the small work done is given by dW is equal to F into dx. F is equal to Kx, Kx dx. Suppose that the spring is extended from 0 to x, 0 to 0.2 x point it is extended, then the total work done is given by small value. When we get the total value can be obtained by integrating the function. Integration already taught in the class, the earlier lessons. You must go through those videos also, right? Total work done W is equal to integral 0 to x f dx. F is equal to what? Kx dx. This is a very important relation, potential energy of a spring. What we are going to calculate, very, very simple, right? That is, K is a constant for a spring, K into integral 0 to x, x dx. Integral x dx is equal to x square by 2. Therefore, this is equal to x square. K into, this is equal to K into integrated means s square divided by 2. Yesterday also I mentioned this 0 to x. That means integral x raised to n dx is equal to x raised to n plus 1 divided by n plus 1. This is the theory. Here it is x raised to 1 dx in place of